In this problem, we're going to work with a boundary value problem. So it says find the values of lambda for which the given problem has a non-trivial solution. Also determine the corresponding non-trivial solutions. And the problem they give you is y double prime plus lambda y equals 0, y of 0 equals 0, y prime of pi equals 0. So before we do this problem, let's make sure we understand what the question's asking. So lambda is a real number, and it shows up in this differential equation here. It's the constant that's being multiplied by y, and we're given these initial, or these boundary conditions that y of 0 equals 0 and y prime of pi equals 0. So they tell you what happens at 0, they tell you the value of y, but then they tell you at pi the value of the derivative and not the original function. So we want to find what numbers lambda make this boundary value problem have a non-trivial solution. So non-trivial solution, what does that mean? Well, the function y equals 0 satisfies this differential equation. Because if you just have the function y equals 0, then y double prime is 0, and if you add 0 plus lambda times 0, you get 0. And when you plug in 0 into the 0 function, you get 0. And also the derivative of the 0 function is the 0 function. When you plug in pi, you get 0. So the 0 function satisfies this differential equation, no matter what lambda is. So they want you to find what values of lambda will make this differential equation have a solution other than the constant function 0. So the trivial solution is the constant function 0. Non-trivial solution means any function, any solution that's not just the 0 function. And then, so once you figure out what lambdas will give you non-trivial solutions, the question also asks you to find what are the non-trivial solutions for those lambdas. Okay, well, there are three cases. So we're going to have to find the characteristic equation for this differential equation. And we know that the characteristic equation is going to be r squared plus lambda equals 0. But the roots, the values of r that make this true, are going to depend on whether lambda is positive, negative, or 0. So we actually have three cases. So let's work with case 1, which is when lambda is positive. And then case 2 will be when lambda is 0, and case 3 will be when lambda is negative. So we're going to get three different things we have to do, because the general solution is going to depend on the different cases. So case 1 is if lambda is positive. So we have r squared plus lambda equals 0. I'm just rewriting it. And this time, well, if you subtract lambda, you get r squared is a negative number. So now you know that your r has complex roots. Your r has complex values. It's going to be plus or minus I times the square root of lambda. Right? Because, I mean, just if it helps, just pretend that lambda is like 5. So if r squared is negative 5, what's r equal to? It will be plus or minus I times the square root of 5, right? So whatever lambda is, okay, whatever that number is, instead of 5, you would just have lambda. So you get r equals plus or minus I times the square root of lambda. I'm just going to erase this. Oops. So the general solution is going to be y equals c1. So you have this 0 plus or minus I root lambda, right? So your alpha, if you write this root as alpha plus or minus I beta, it's alpha equals 0, beta equals the square root of lambda. So you get c1, this e to the alpha t is just 1. So you get c1 cosine beta t, so it's square root of lambda times t. And notice that I put the little vertical thing under the square root because I want to remind myself that the t is not inside the square root. So I get this, plus c2 times sine times the square root of lambda t. Now that's my general solution to the homogeneous equation. Now I need to plug in my initial conditions or my boundary values. So when I plug in y of 0 equals 0, so I plug in t equals 0 and get y equals 0. So that gives me 0 equals, so when I plug in t equals 0, I get cosine of 0, that's 1. So I get c1 plus, then when I plug in t equals 0, I get 0 times c2 is just 0. So I get 0 equals c1. That's what I get from the first condition. Now I look at the next condition, y prime of 0, y prime of pi equals 0. Okay, well, actually, since that involves the derivative, I need to find a derivative. So maybe I should have found the derivative first. So I'm going to find y prime, and that's going to give me, let's see, negative c1 times the square root of lambda times sine of the square root of lambda times t, right? By the chain rule, I have to take the derivative of the inside. And then I get plus the square root of lambda times c2 cosine square root of lambda times t. So the first condition, I already plugged it in, tells me that c1 is 0. So when I plug in, okay, my pi, I'm plugging in pi into y prime of t. So y prime of pi equals 0 is going to tell me what? Well, my c1 was 0. So this c1 is 0. So actually, I don't need to worry about that part. All I have left is the part with the c2. So when I plug in t equals pi and set the result equal to 0, I get 0 equals the square root of lambda times c2 times cosine of the square root of lambda times pi. Now this cosine of the square root of lambda times pi doesn't simplify because lambda might not be, the square root of lambda in general is not an integer, right? So it's not like cosine of pi and cosine of 2 pi or anything like that. It's like cosine of, the square root of 3 pi or something, or the square root of e pi or something, right? It doesn't, the square root of pi, the square root of lambda is just a real number. So if you have a cosine of real number times pi, that inside real number times pi doesn't in general have a nice cosine. So you can't simplify this at all. Okay, so 0 equals the square root of lambda times c2 times cosine of root lambda pi. Well, does that imply that c2 has to be 0? Not necessarily. So it could be that cosine of root lambda times pi could be 0. So if that is the case, then c2 doesn't have to be 0. And what that means is that you don't necessarily have to get y is the constant function 0. So this is going to have, this equation has non-trivial solutions if, so the equation has non-trivial solutions if cosine of root lambda pi is 0. Now the question is, what lambdas will make cosine of root lambda pi equal 0? Well, we have to think about what values are going to make cosine equal to 0. So now we go back to our trig function. So we know that cosine, as you go around the unit circle, it goes 1, 0, negative 1, 0. And then back to 1. So the values that will make cosine equal to 0 are pi over 2, 3 pi over 2, and then you just keep adding pi. So the inside root lambda pi is going to be pi over 2 plus, so let's see, you're adding pi each time, right? So it's going to be pi over 2 plus pi k, where k is any integer. It could be 0, positive, or negative. So hopefully you're familiar with how to do this when you took trigonometry, right? What are the, cosine of x equals 0, solve for x. The answer is pi over 2 plus pi k. where k is any integer. So now we have to figure out what lambda is, so we divide both sides by pi. So we get square root of lambda equals 1/2 plus k. And then you square both sides. So lambda is going to be, okay, I'm going to write as k plus 1/2 squared, where k is any integer. So these values, these positive values of lambda, are going to give you non-trivial solutions. And what are the non-trivial solutions? Well, let's see. So we have the general solution here, right? But the first condition tells us that C1 is 0. So this whole thing's going to be 0. And then you're just going to have constant times the sine of root lambda t. So let's just remind ourselves. So let's just summarize what's happening. So if lambda is k plus 1/2 squared, where k is an integer, then cosine of root lambda pi is going to be 0, right? And so no matter what C2 is, this is going to be a solution. This C2 sine root lambda t is going to be a solution to your equation. So these lambdas will give you non-trivial solutions, and then the non-trivial solutions are going to be y equals C2. Well, we only have one constant, so let's just write that as C sine of root lambda t, where C is not 0. Because if C were 0, then this would just be a constant function, right? And we want the non-constant function. We want the non-zero solutions. I mean, if C were 0, then you would just have y is the 0 function. And we're asked, what are the functions other than the constant function 0? So we get y equals C sine of root lambda t, where C is not 0. Okay? Or you could, I guess you could replace the lambda with k plus 1/2 squared. So then that would give you C sine k plus 1/2 times t. Okay. Okay, but I think it's just more natural to write it in terms of lambda, because they're asking you what lambdas will give you non-trivial solutions. We found them, and then the solutions are going to be that in terms of lambda. Okay, that's case 1. So we're not actually done with the problem, because we only did case 1, which is we considered what happens when lambda is positive. We found that there are certain lambdas that give you non-trivial solutions. So now we have to do case 2. Well, case 2 is when lambda is 0. So when lambda is 0, then you just get y double prime equals 0, right? Because we're plugging in lambda equals 0 into this differential equation. You just get y double prime plus 0, y equals 0. That's just y double prime equals 0. Well, that's easy to solve. You just take the antiderivative twice. So y prime is a constant, because the derivative is 0. And then you take the antiderivative again. So when you integrate the constant, you get the constant times t plus another arbitrary constant. So the solution is C1t plus C2. Now we plug in the initial values. So y of 0 equals 0 tells you, well, you get 0 equals C1 times 0 plus C2. So C2 is 0. Okay, what does the condition that y prime of pi equals 0 tell us? Well, y prime of 0, y prime is just the constant function C1. So when you plug in pi into the constant function C1, you just get C1. So you get 0 equals C1, right? Are we okay on how we get this? Because y prime of pi, that's C1, and then we're given that is equal to 0. So C1 is equal to 0. So if lambda is 0, then the boundary conditions tell us that C1 and C2 have to both be 0. Well, if C1 and C2 are both 0, and your general solution is C1t plus C2, what does that tell you? If you replace C1 and C2 by 0, you just get y equals 0. That's the constant function 0. So lambda equals 0 does not give you a non-trivial solution. So the only solution when lambda is 0 is the trivial solution, y equals 0. No non-trivial solutions here. Then the final case is case 3, which is when lambda is negative. So since lambda is negative, let's write it as negative a, where a is positive. So for example, if lambda is negative 4, then your a would be positive 4. You don't have to do this, but I think it's just easier to work with. Because when you work with a variable, it's easy to kind of assume that it's positive. So if you write t, or lambda, it's natural. I think a lot of students assume that it's positive, even though it's not, right? So if you just write it as negative a, or a is positive, it just reminds you, it's easier to work with. So anyway, let's go back to the characteristic equation. We know it's r squared plus lambda equals 0. That's true in all the cases, because you have the same differential equation. So in terms of a, that's r squared minus a equals 0. A is positive, so r squared is a. So now you have r squared is a positive number, so you're going to get 2 real roots. You just get r equals plus or minus the square root of a. So now the general solution is y equals c1 e to the square root of a t plus c2 e to the minus square root of a t. And let's take the derivative because we're going to need to plug stuff in. So you take the derivative and you get square root of a times c1 e to the square root of at minus the square root of a c2 e to the minus square root of at. So now we plug in our initial or boundary value conditions. Y of 0 equals 0 into the first equation tells us that 0 equals c1 plus c2. Because e to the 0 is 1, right? Now we plug in what we know that y prime of pi equals 0. So that's going to give us 0 equals the square root of a times c1 e to the square root of a times pi minus the square root of a c2 e to the minus square root of a times pi. Okay, what can we do with that? So if you look at the second equation, what can we do to simplify this? I mean, look at the constants here. We have a square root of a times c1 times e to the root a t. Root a pi. What am I doing here? Oh, I just somehow replaced the pi with the t's with pi's. Wow. Yeah, that should be a t. Right, I have a root a, and then this e to the minus root a t. I guess the e to the root a t and e to the minus root a t's don't cancel. But the square root of a, I can divide both sides by the square root of a, can't I? So that's going to give me 0 equals c1 e to the... Oh, wait, no, it is pi. It is pi because I plugged in t equals pi. Oh, man. Okay. Well, c1 e to the root a pi minus c2 e to the minus root a pi. And I also am given that 0 equals c1 plus c2. All right, now I need to solve for c1 and c2. I mean, there's a bunch of different ways of doing this, but I guess the easiest way would be to work with the second equation. C2 is minus C1, and then plug that into the first equation. So I get 0 equals C1 e to the root a pi minus C2, so that's plus C1 e to the minus root a pi. So I get C1, I can factor out the C1, e to the root a pi plus e to the minus root a pi. Well, what does that tell me? So I have 0 equals C1 times some constant. Now, is this constant equal to 0? No, it's not equal to 0, because e to the root a pi is never going to equal e to the minus root a pi. It's not going to equal negative e to the minus root a pi. So one way to think about this is that e to anything is going to be, well, e to any real number is going to be positive, right? So that's a positive number. E to the minus root a pi is also going to be a positive number. So when you have two positive numbers, you add them, you get a positive number. So I have 0 equals C1 times a positive number. What does that tell me? That tells me that C1 is going to be 0, right? Because I can divide both sides of the equation by this constant, this positive constant, and get that C1 is 0. So if C1 is 0, then what does that tell me about C2? Well, C2 was negative C1, so C2 is also 0. So what does that tell me? Once I find that C1 and C2 are both 0, what does that tell me about my function? What does that tell me about my y? It must be 0, right? It must be the 0 function, because when you replace C1 and C2 by 0, you just get y equals 0. So that means that you have, in case 3, you have no non-trivial solutions. The only solution is y equals 0. So no non-trivial solution. And so now that we've done all three cases, we are finally done with the problem. The question says, what are the values of lambda for which the problem has a non-trivial solution, and what are the corresponding non-trivial solutions? Well, the answer is that the lambdas are the values k plus 1/2 squared for any integer k. So what would these numbers be? Well, if k is 0, you get 1/4. When k is 1, you get 9/4. When k is negative 1, you get, I guess you get 1/4 again. If k is negative 2, you get whatever. You get a bunch of values. Those are the lambdas. And then those are the lambdas to give you non-trivial solutions. And then the non-trivial solutions are the functions y equals a constant times sine of root lambda t, where the constant is not 0. And then all the other cases, when lambda is 0, when lambda is negative, those only give you trivial solutions. So that's the answer. So a long problem, but it's actually not that bad once you see how to do it. You just have to remember that you have three different cases, depending on whether lambda is positive, negative, or 0, and then you just have to plug in your boundary conditions and then see what that tells you about C1 and C2. And you just have to be careful when you have something like, if you have this equation, 0 equals root lambda C2 cosine root lambda pi, that doesn't necessarily mean that C2 has to be 0, because one of the factors could be 0. But in the other case, so if you go back to the last case, right, here we had 0 equals C1 times something, but no matter what your A is, okay, the point is that no matter what A is, this factor has to be positive. That's the difference between this and then the previous case where lambda was positive. Okay, that's all for this video.